So this next lemma in section 3.5 is specifically about right angles or obtuse angles in a triangle. So if we know the sum of all the interior angles is equal to 180 and one angle is 90 degrees or more, we would know that the measure of angle C, the one that's 90 degrees or more, has got to be greater than the measure of either of the other two angles if the sum is going to equal 180. So hopefully you're getting the idea that the big is always bigger than the smalls. The big is always bigger than the pieces. All right, and here we have the addition property of inequality. If I'm comparing two values and A is bigger, and I'm comparing these two values and C is bigger, the sum of the biggers is always going to be greater than the sum of the smallers. If I add the two large values together, that's always going to be bigger than adding the two smaller values together. And we'll see an example of that down here. Okay, so we are told that the length of AB is bigger than the length of CD. So AB is bigger than CD. We're also told that the length of BC is bigger than DE, and they want us to prove that AC, this purple segment, the length of AC, prove that that is bigger than the length of the segment CE. And you can't just say, we'll look at it. I mean, we have to prove it. All right, so we were told that the length of AB is bigger than the length of CD. And you know what? AB plus BC is going to equal AC. AB plus BC is equal to the length of AC. That's my purple segment that I'm trying to find the length of. I'm also told that BC is greater than DE. And you know what? What is CE made of? CD plus DE is equal to CE. So which one is bigger? AB is bigger than CD. BC is bigger than DE. AB is bigger than CD. BC is bigger than DE. These are the two larger segments in these comparisons. So therefore their sum, when you add them together, must be larger than the sum of the small ones. So we can say, yes, AC is greater than CE, because it's made of the two larger segments, or longer segments, I should say, longer. All right, moving along. Let's just talk about the relationship between, in a single triangle, the relationship between the sides and the angle measures. And this is true for any triangle. Okay, so if I have triangle A, B, C. Here I'm going to have my angles. They are all uppercase. And here I'm going to have my sides. These have the same name but lowercase. Here's side A, here's side C, and here's side B. the largest angle is always opposite the longest side. You know what? The smallest angle is always opposite the shortest side. Which leaves the middle angle, the one, it's not the largest, it's not the smallest. The middle angle is always opposite the middle side. The side that's not the longest, it's not the shortest. This will always hold true for any triangle. So this lemma is talking about side lengths. Side lengths. If one side of a triangle is longer than the second side. So let's say this is 20 and this is 8. I may not know much else about this triangle, but if side B is bigger than side C, which it is, that tells me that the measure of angle B is bigger than the measure of angle C. The longer side is opposite the bigger angle. The shorter side is opposite the smallest angle. So this is for all the sides of a triangle. So let's take a look here. Let's look at this. Here's an 80-degree angle and here's a 40-degree angle. If the measure of angle A is 80 and the measure of angle B is 40, what are the lengths of side A and side B? Well, since the measure of angle A is bigger than the measure of angle B, that must tell me that side A is bigger, longer than side B, which tells me CB is greater than AC. And I made a mistake there. We should not have, we're talking about the measure, so we do not want the bar up there. The measure of segment BC or CB is greater than the measure of AC, using the inequalities. So the last lemma started with side lengths. If you know one side length is the longest, you know that angle is the biggest. This one starts with, if you know one angle is the biggest, you know the opposite side is the longest. It's basically a corollary. Moving on, a perpendicular line segment from any point is always going to be the shortest segment that can be drawn. So if here I have a line and here I have a point, how many lines can I draw from the point to the line? Well, there's that one, but that's not the shortest distance. Well, there's that one, but that's not the shortest distance. The shortest distance is always going to be the perpendicular segment from the point to the line. That's always going to be the shortest, and any other segment will always be longer than the perpendicular line that was drawn. And everything we've said about points to lines can also be said through planes. Through planes. So the shortest distance from a point that's not on the plane down to the plane is always going to be the one that creates a right angle. So the last inequalities that we want to talk about are in a single triangle, what's the relationship between the side lengths? You have three side lengths, A, B, and C. side length A is always going to be greater than the difference of the other two sides, and it's always going to be less than the sum of the other two sides. So if you have a valid triangle, if you have a polygon that has three sides that meet at vertices, any side length is greater than the difference of the other two and less than the sum of the other two. So if I were to look at side B, I know that's always going to be greater than the difference of the A and C sides and always going to be less than the sum of the A and C sides. And I might as well put this down here. If we're talking about side C, the other two sides are A and B. That's the triangle inequality theorem. So another way to say that is the length of any side of a triangle must lie between the sum and the difference of the lengths of the other two sides, greater than the difference, less than the sum.